Welcome to our presentation. In this presentation, we will be reviewing about the article on hydrogen production, storage, utilization, and environmental impacts that is published by Osman and his colleagues at 2021. I'm Putri, together with Tan Kaisang, Aisyah, and Tang. We will be working to to explain more about this article. Hi, I'm Putri QISTINA. In this presentation, we will be talking about the overview of the article, three main critiques, reflection on the use of AI, and key takeaway messages. So, I'll be sharing insights from a comprehensive review by Osman and colleagues on hydrogen's role in sustainable energy development. As global energy demands rise, hydrogen stands out as a clean energy vector. Its demand is expected to increase from 70 million tons in 2019 to 120 million by 2024. The review explores several production methods including electrolysis, steam methane reforming, and methane pyrolysis. Each has unique environmental impact which the authors assess using life cycle analysis. This provides valuable comparison metrics to guide decision-making. Hydrogen's applications span across power systems, transportation, ammonia synthesis, and metallurgical processes. To ensure reliability, strategic storage solutions such as underground reservoir and salt caverns are also discussed. Ultimately, the article stresses the importance of integrating sustainability assessments and infrastructure planning to support hydrogen development aligned with global climate goals.
Hi, so today I'm going to explain about three main critiques regarding our article. So first is highly comprehensive review. So first of all, this article already summarized 24 recent life cycle assessment studies, and then this also provide decision makers with nuanced insight into the hidden environmental costs of both renewable and non-renewable hydrogen pathways. And then next, for clear comparison across technologies, the review doesn't just list numbers, it also offers qualitative insight into why certain technologies perform better or worse. And then the last but not least is lack of geographic and socioeconomic contextualization. So most examples are Eurocentric or generalized, with little consideration of how hydrogen adoption differs in low and middle income countries or regions with limited renewable capacity. For instance, green hydrogen is more feasible in areas with abundant renewables, while steam methane reforming may still dominate in fossil fuel-rich regions.
For the reflection of the use of AI, firstly, I found AI to be quite helpful. It allowed me to summarize complex articles more quickly, clarify unfamiliar scientific terms, and give me ideas on how to summarize my critique. In that sense, AI helped save time and support my understanding of the content. However, I also discovered some limitations. Some of the AI-generated responses were too general or entirely accurate. I had to double-check everything with the original article to make sure the information was reliable. This reminded me that AI cannot replace proper reading and critical analysis. I also became more aware of ethical concerns. It was important for me to ensure the work remained my own. Maintaining academic honesty was a key part of the process. I use AI as a support tool, not as a way to avoid thinking or writing for myself.
Hello everyone, now I'll present the four main key takeaways from our critique of the article. First, clean doesn't mean impact-free. The article promotes green hydrogen as the cleanest option, but also shows that even green hydrogen has hidden environmental costs. For example, producing solar panels or processing biomass still emits greenhouse gases. So calling this a green method isn't a suitable way if you consider the whole life cycle itself. Secondly, electrolysis is not yet an affordable way for us to produce hydrogen. Water electrolysis is powered by renewable is one of the cleanest way to produce hydrogen, but it's an extremely costly way. For information, less than 5% of global hydrogen production is using this way to produce. And it's way that requires a lot of electricity and expensive equipment, which limits the practical use on large-scale projects. Third, storage remains a safety concern that storing hydrogen is another big challenge as it's a flammable and lightweight gas that could leak easily, potentially cause explosion, and weaken the metal pipes as it due to its corrosive properties. This technical and safety issue makes large-scale storage both complicated and risky. Fourth, limited global applicability. Most of the studies reviewed in this article are based on developed countries like Europe, but hydrogen infrastructure, energy access, and policies vary greatly across regions. This makes the article finding less relevant for developing countries where conditions are different and local data is lacking. In summary, while the article gave a strong technical overview of hydrogen energy system, its real-world value is reduced by high production costs, safety risks in storage, and lack of regional inclusiveness. To move forward, future research should focus on cost reduction, safer storage method, and region-specific solution. So that's all for my part. Thank you.